Yeah, yeah. So. Thank you.
Anything else? Everything's fine?
Everything perfect. Thank you. Good morning, everyone. Can you hear me? I think it works. So I think we can start. First of all, thank you all for being here today for the tutorial From Pixels to Answers, Leveraging Pythia for Earth Observation Intelligence. I'm Despina Athanasia Pantazi, and today I will present to you this tutorial with my colleagues Sergios Anestis Kefalidis and Kostas Plas, who will be here for the next presentations. So to start, we will give an overview of the tutorial. First of all, we will have an introduction about the team, the artificial intelligence team that I'm part of, as well as my colleagues. Then we will give an overview of the satellite event, and then we will proceed with the technologies overview, where we have 5 different parts for the different steps of the tutorial. So let's start with the introduction. First of all, our team is called Artificial Intelligence Team. It's from the National and Kapodristian University of Athens, the Department of Informatics and Telecommunications, and our supervisor is Professor Manolis Koubarakis. The team was established in 2012. It is an academic team, and we are about 15 people. You can find more information by following this link. So what is our core expertise and technology domain? First of all, artificial intelligence. Then we focus a lot in the area of Earth observation, in question answering for knowledge graphs, which we will explain in a bit if you haven't heard of them, and artificial intelligence for the public sector. So, our research activities, products and services include semantic technologies for satellite data. We include deep learning and, of course, natural language processing, which you will see today as well. We include databases and artificial intelligence for the law. So some of the major space-related projects that we were involved in are Fair to Adapt, which is actually a current project that we are involved, AI for Copernicus, Extreme Earth, and DA for DTE. All of this can be found on the web. If you need more information, of course, you can ask us directly. Some of our main partners are the European Space Agency, the National Observatory of Athens, and the European Centre for Medium-Range Weather Forecasts. And some of our main customers are the European Space Agency and the users in the different European projects that we are involved in. So here you can see an overview of the pipeline where we get images from satellites, and we conclude to make this information available for search, browsing, exploration, and visualization. So with green here, the green overline, you can see the steps that our team is involved in, and we start after the ingestion, the processing and the catalog archiving. We start with dataset discovery, we continue with knowledge discovery, and then we transform this information into RDF, which we will explain in the next slides, in case you don't know about it. Then we interlink this information in order to make it more valuable for the customers. We publish this information, and then we storage, query, and question answering. Lastly, we make it available in order to be searched, browsed, explored, and visualized. So some of the strategic priorities that we have are the development of knowledge graphs, question answering engines, and chatbots for the space domain. And our long-term vision is to apply modern artificial intelligence techniques to Earth observation. And of course, we want to implement applications with societal and economical value. So we will proceed with a satellite event overview. So as you already know, recent advances in satellite technology have enabled frequent high-resolution and global-scale monitoring of the Earth. So this explosion in the availability of Earth observation data presents opportunities to support critical societal challenges. So artificial intelligence, knowledge graphs, and semantic technologies are emerging as powerful enablers to bring the gap between raw Earth observation data and actionable insights. So in this tutorial, we will walk you through the full pipeline of how we can build intelligent Earth observation services from ingesting raw satellite data to creating responsive natural language-powered applications using technologies and tools that are being applied to research projects like Fair to Adapt that I mentioned. So this event is hands-on, so you can learn by doing, while also we will offer a blueprint that can be replicated across other regions and domains. So it is a half-day tutorial, so 3 hours. We start with the introduction, the presentation that I'm giving right now. We will proceed with the first and the second parts, where we will go from unstructured Earth observation data to RDF with Python, and how we can store and query it with GraphDB. We will have a short coffee break, and then we will proceed with how we can pull down the sparkle barrier for RDF access. We will continue with the part 4, which is the visualization of the results using the tool Leaflet. And finally, we will optimize for real-time performance by query execution optimization with the tools Jedi Spatial and Ghost. So, just to summarize, the tutorial will cover tools and methodologies to transform raw Earth observation data into semi-structured RDF data, which can be easily and efficiently queried by both novice and expert users. So, although the tutorial will be grounded in a use case focused on Hamburg, Germany, the methodologies and tools presented are generalizable to Earth observation scenarios across many different domains and geographies. So if you have any ideas, of course, you can discuss them with us in order to support you and give you these technologies, which are open source, for your domains and for your specific geographical locations. So you can follow along hands-on during the tutorial session and execute the code in real time. And we will provide runnable code checkpoints to ensure that you can easily set up your environments and follow the tutorial without any issues. And of course, we will be present for you to answer any questions that you probably have. And then we can continue to the technologies overview, the 5 different parts and the technologies that they have. And first of all, part 1 is about how we can go from unstructured Earth observation data to RDF with Python. So our starting point is to take raw Earth observation datasets, specifically satellite images with accompanying metadata, and how we can convert this information into the RDF format using a simple ontology. So just to be specific here, we will use OpenStreetMap data, or OSM data, and satellite images from Sentinel-1 and 2 which are provided by the project DA4DTE and are used in the project FAIR to adapt. So how can we do this transformation? We will use ToposKGlib, which is a custom semantic parsing library developed by our group, and it is capable of extracting structured knowledge from unstructured Earth observation data. So ToposKGlib is part of the Topos framework, and its toolchain for handling common tasks in knowledge graph construction and interlinking. So these tools are made available with a Python library, a desktop application, and a chatbot implementation through the LLM function calling. So you can find more information by following this link. And of course, you will have all these presentations available to just have all these links that will be included here. So, Topos framework was also used to develop ToposKG, which is a comprehensive geospatial knowledge graph that integrates, first of all, topologically consistent administrative division data, general purpose geospatial information, and natural resource data, including lakes, rivers, forests, and mountains. So just to have an overview here of the data, for example, from OSM, we have water bodies, which are more than 12 million entities, and this is about 34 gigabytes in the disk. Or, for example, we have points of interest, which are more than 43 million entities and are about 14 gigabytes in the disk. And all this information is included as well. So, I've talked a bit about RDF, but what is it? In case you haven't heard of it, the Research Description Framework, or RDF, is a data model for representing information, especially metadata, about resources in the web. So, RDF is intended for situations in which information about web resources needs to be processed by applications rather than being only displayed by people. So, RDF is based on the idea of identifying resources using web identifiers and describing resources in terms of simple properties and property values. So, how do we do this? To identify resources, RDF uses Uniform Resource Identifiers, or URIs, and URI references. And the resources being described have properties which have values. So, what is the terminology? We have three different parts. This is very important because we talk about triples. This is the structure of the RDF. The first part, the part that identifies the thing the statement is about, is called the subject. The part that identifies the property or characteristic of the subject that the statement specifies is called the predicate. And lastly, the part that identifies the value of that property is called the object. So we have triples for statements that have a subject, a predicate, and an object. So for example, how can we represent this fact that you see here in RDF? So we have one movie, Mulholland Drive, which has as the director David Lynch. So here, if we wanted to represent this information in RDF, we would have a triple with a subject, a predicate, and an object, where the subject would be the Mulholland Drive film, the predicate would be has director, and the object would be David Lynch. So this is our triple here. Then we can have RDF graphs, where RDF models statements by nodes and edges in a graph. So, if we wanted to have an RDF graph notation, a statement is represented by a node for the subject, a node for the object, and how we can connect them with an edge for the predicate. So, this is directed from the subject node to the object node. And if we want to see an example of an RDF graph here, for example, we have Bob here, who is a person, so this is already a triple here. Subject, predicate is a object person. Another triple is is a friend of Alice. So Alice here is the object and the predicate is a friend of. Bob is interested in Mona Lisa. And another triple could be Mona Lisa was created by Leonardo da Vinci. So this is the idea. We have triples if we want to represent information in RDF. So, being a powerful and expressive framework for representing data, RDF is used for building knowledge graphs, which were mentioned in the introduction in the first slides. So what are knowledge graphs? They are richly interlinked, interoperable, and flexible information structures. So the heart of the knowledge graph is a knowledge model, which is a collection of interlinked descriptions of concepts, entities, relationships, and events, where descriptions have formal semantics that allow both people and computers to process them in an efficient and unambiguous manner. They have descriptions that contribute to one another and form a network where each entity represents part of the description of the entities related to it. And we have diverse data which is connected and described by semantic metadata according to the knowledge model. So we will continue with part 2, which is about storing and querying RDF data with GraphDB. And what is the situation here? From the first part, we already have some newly formed RDF data. So in part 2, we will start from this information, and along with geospatial data concerning administrative divisions and natural features, we will load all this information into GraphDB. In addition to the built-in GeoSparkle support, we present a plugin for supporting STSparkle, which is the query language for RDF representations. So these extensions allow the representation and querying of geometries, such as points, polygons, and more, using geospatial functions, making GraphDB ideal for storing Earth observation data with spatial dimensions. So just a bit more information about GraphDB, and then Kostas will explain more in his presentation. On-to-text, GraphDB is a highly efficient, scalable, and robust graph database with RDF and Sparkle support. So it is one of the few triple stores that can perform real-time semantic inferencing at scale, which is very important in today's technologies. So then we will continue with STRDF, which is an extension of RDF for the representation of geospatial information that changes over time. So, as I mentioned, STSparkle is the query language for STRDF, and it includes spatial data types which are introduced, as I mentioned. We have geospatial information which is represented using spatial literals of these data types, and we have OGC standards, well-known text, and geography markup language, WKT and GML, which are used for the serialization of spatial literals. And you can find more information if you follow this link to read the relevant paper about STRDF. So let's see an example here. So an STRDF triple is derived from geonames that represents information about a Greek town which is called Olympia, which includes an approximation of its geometry. Just a bit more information about geonames. It is a geographical database that covers all countries with more than 11 million place names. And this data is available for downloading free of charge. So here are the namespaces of the URIs that I mentioned before when I was talking about RDF. In order to just have a namespace here and don't include all the URI, the full URI, which would have the triples represented below, a bit more complex. So we have RDF, STRDF, which is represented in triples, as I mentioned. So we expect a subject a predicate, and an object for each statement that we want to represent. So here we have this subject, which is an entity for the town Olympia. The predicate here is the name, and the object is Olympia. So this entity has as a name the name Olympia. If we want to have more statement for the same subject, in RDF we can use the semicolon here and just provide the predicates and the objects later without the need to repeat the subject here. So this entity is also a town and has as a geometry a specific polygon, which is represented in WKT. So here we have three triples, one for the name, one for the type, and one for the geometry. Then we have three more triples produced from the processing chain of the National Observatory of Athens that represent burned areas. So we have three different burned areas, two triples per area, where we have the specific area, which is a burned area, and has a specific geometry. So we have three different polygons for three different areas. So how we can combine the previous information that I mentioned, the town of Olympia, which has a specific geometry, and some more information that we have for burned areas. We can demonstrate the functionality of ST-Sparkle by posing the query, return the names of towns that have been affected by fires. So how can we do this? We use ST-Sparkle to get this information about the triples that I mentioned before. So we select the name, where the town is a town, has a name, a specific name. This is a variable, a placeholder for the name that we want to return, and has specific geometry. This is about the town, the first three triples. Then for the burnt areas, the variable for the burnt areas, we have that this has as a type a burnt area and a specific geometry. And how we can filter this? We say to the ST-Sparkle query, filter this information, the two geometries that I mentioned before, in order to overlap and see that the town is also a burnt area. So if we execute this query, we will get as a result the town Olympia. So this is very similar to SQL if you have already seen this. We will see more of these examples in the next presentations as well with the data that we will use. Then we will proceed to part 3, where we will have natural language interface by employing Pythia, the tool Pythia. And what is the situation here? We already have the RDF data, which is ready, and you will integrate the tool Pythia, a geospatial, spatially aware question answering engine that is designed to function as a plug-and-play question answering solution for general purpose and specialized knowledge graphs. It does not require fine-tuning, which makes it a viable solution for use cases that lack training datasets. So to achieve this, Pythia introduces a novel combination of agentic reasoning and bidirectional graph search to identify and explore connections between nodes relevant to the questions. So extensive experiments show that Pythia achieves state-of-the-art performance on multiple datasets and knowledge graphs, along with transferability and the ability to handle geospatial queries. All this will be presented by my colleague Sergius. So, I think it is important to mention here the tool TerraQ as well, which is a text-to-Sparkle system which provides a natural language interface for RDF stores. It does so by translating natural language questions into semantically equivalent Sparkle queries. So, what is TerraQ? It is a question answering engine that simplifies interaction with Earth observation data by removing the need for users to understand Sparkle. So as a result, Earth observation data is made more easily accessible to users, while maintaining accuracy and computational efficiency. So it interacts only using only natural language, so no expert knowledge is required. It uses Sentinel mission images, and it has access to 1.5 million Sentinel-1 and 2 images of Europe. It is built using a range of industry standard and custom built tools to ensure a rapid execution. And of course, a very important aspect, it is open source. If you want to have more information about this, you can attend to tomorrow's presentation, which is a multi-agent system to orchestrate interactions with digital twins of Earth, which is tomorrow at 11:45. So, part 4 is about visualizing geospatial results with Leaflet. So until now, results are represented in raw CSV-like formats. So when dealing with satellite image data, it is important to be able to see the images and their visualization on a map. So how can we do this? We saw how such functionality can be implemented using the tool Leaflet, which is an open source JavaScript library for interactive maps. It works efficiently across all major desktop and mobile platforms, and it can be extended with plugins, and it has a well-documented API. Now for the last part about the query execution optimization and ZEDI spatial and Ghost, we will showcase the complexity of geospatial calculation when using large polygons. So this is very important because these large polygons and geometries generally make all the application very slow. So we have long response times, which is not very good for us. So to deal with this, we employ geospatial interlinking and query rewriting to speed up query execution. And we do this using the tools ZEDI Spatial and Ghost. So, just a bit information about this. Kostas will explain this to a lot more in his presentation. ZEDI Spatial is an open source system for computing topological relations according to the DE9IM model between datasets with geometric entities. And the tool Ghost, which stands for GeoSparkle to Sparkling Transpiler, is a transpiler for converting GeoSparkle queries to the Sparkle queries using geospatial materialized relations. You can find more information about the ZEDI Spatial here, and we will provide also links for the Ghost tool as well. So thank you very much. This was the introduction, and we will proceed with Kostas and the first two parts of the tutorial. Thank you.
So I have just a small presentation, nothing too much. Okay. You hear me? No? Good morning again, everyone. We're moving. Yeah, that's probably better. We're moving to the technical part of the tutorial. Just a very, very small lecture. I won't take too much of your time, too much of the coding time for this. Just a bit of an overview for part one and part two of the tutorial. As Despina already said, part one is our goal here is to take Earth observation data. Okay, what is this Earth observation data? It's data about Hamburg, okay, the city of Hamburg, and some geospatial information like points of interest in the city, some rivers that cross the city, and the Earth observation part is Sentinel-1 and Sentinel-2 data, okay, retrieved from the repositories of one of our projects with the European Space Agency, with ESA. And our goal here is to use ToposKG, this library, to take these files, which are in GeoJSON format, which I'll explain a bit later, and to transform them into RDF data. Okay. So, what GeoJSON is, and I don't know if it's too clear here. Yeah. Okay. GeoJSON is basically an extension of JSON. Okay. I don't know if anyone's familiar with this technology, which basically specializes in transforming and representing geospatial features. If that's not too clear, I can show you another example. That should be better. That's better, right? Okay. So, what are GeoJSONs? GeoJSONs are just JSON files, okay, that have a bit of a more specific structures, so we can know clearly what is and what isn't the geospatial information. So, in this file, you see here this geometry key. Let me zoom in a bit. Okay. So, here is the geometry. Okay, that part, that field of the JSON file represents the geometry. What is this geometry? It's a point on the map. Okay, and this is these coordinates. So for more information, for thematic information, we have the properties key, which basically says additional information, some metadata for the given entity. For example, a location's name, etc., etc. Okay, so we're going to be working with this kind of geospatial files in this tutorial, and we want to transform them into RDF data. Okay, what is the target RDF data here? The target RDF data is, like Despina showed you before, some triples. Okay, we're going to use the GeoSparkle reference format. So we have an entity. This entity has a geometry, which is another entity in itself, and this geometry has a WKT representation. Okay, a WKT representation of a geometry is something like this. Okay, it's like a point and its coordinates, a line string and a pair of coordinates, like a polygon and the edges, the coordinate edges. Okay, so that's it for the first part. We are going to be writing a bit of Python code. Okay, ToposKG library is a Python library. For anyone that hasn't seen the link, you probably didn't have access to the link. You can install the library using a pip. It's a pip install ToposKG. Okay, this library has some parsing capabilities, specifically two right now. The first approach is a naive approach that simply does a mapping on its own to transform the JSON or some other data source into RDF data. And the second one is using mappings. And okay, so we can move forward with it. First of all, I don't know if anyone wants to follow along, they can install the library and we can start coding. I'll give you like 2 or 3 minutes for each step so you can follow along. It's a tutorial, you know, we want you to write code. And the first thing I wanted to do for anyone that's using Linux, I hope most of you are using Linux, is to create a directory. Okay, just make a directory named output. We are going to store our outputs in this directory. Okay, and now we can start writing the Python script. So first, I'm importing the Python libraries. Okay, we're going to be using the simple method for converting the files. It's the JSON converter. That's our class. And using this class, we can take as input any data source, semi-structured data source like JSON files, JSON files, XML files. With this class, it's JSON files, and do a simple mapping that we don't exactly know. You can see this mapping, you can change these mappings. It's a defaulted, very simple mapping from the data source to our RDF data. So for this part, as you can see, as Despina explained already, we are using URIs. Okay, what are URIs? URIs basically are a way to identify things on the internet, on the web. Okay, it's a unique identifier. And for a lot of these entities, because we are talking about knowledge graphs and knowledge that is on the internet, if you click them, they're like a browser link. I have an example in the tutorial. You can see here this link. It's a Wikidata link. Okay, Wikidata is a project that takes data from Wikipedia and transforms them into a knowledge graph that is available on the internet. And if you click on that link and open it on the browser, you'll see that it will open a page about the Hamburg in Wikidata. Okay. Don't you have access to the GitHub page for the tutorial? Oh no. Sergius will upload the tutorial. Yeah, sorry about that. Okay. While we do that, let me explain a bit what we're doing here. So this ontology URI and resource URIs are basically our namespaces for something that could be on the internet, for resources. Okay, the ontology part refers to what we could say in an RDBMS setting in SQL databases, the schema, right? This is the keywords that we're using for our schema, for our tables, for our columns, okay? So when we refer to, for example, a property, okay, a property of an entity, we will refer it from the ontology URI. Okay, if we want to refer to an entity itself, okay, for example, a person and person one, okay, or something like that, we'll refer to it from the resource URI. Okay, that's simple so far. If you have any questions, feel free to stop me. So, this is a very simple Python script. It's nothing too fantastic. It simply goes into the output directory to save the results of our conversion. It's nothing, it's just a for loop inside the directory. It iterates through GeoJSON directory. The GeoJSON directory simply holds our data, okay? The data that I showed you before, okay? The ones we're working with. It's the data about rivers, about points of interest, about sentinel images, okay? So, this is the part where I want to say a bit more. Okay, this is where we are using the GeoJSON class, the GeoJSON converter. Okay, what does it take as an input? The GeoJSON file that we want to transform. Okay, the output file that we want to save our data to. Okay, the ontology and the resource URIs. That's it. Okay. Now, if we want to do the parsing and create a knowledge graph and create an RDF graph, all we have to do is call the method parse. Okay, and if we want to export this data to our output file, all we need to do is just call the function export. Okay, this is a black box function. We don't know exactly what the mappings are, but for novice users that are not familiar with RDF settings and knowledge graphs, etc., it is a very easy way to have access to some RDF data. Okay. So that's our script ready. All we need to do now is to run it. So, in the output directory, if you run this code, you'll see that now we have some files that are that have the extension NT. Okay, these are our RDF files. So, for example, this file is the file that concerns points of interest. Okay, if you see, these are triples. Okay, they are a bit lengthy, but don't worry about it. So, this is the subject. Okay, the predicate, the property, let's say, of the entity. So, for example, this resource has a geometry which is another entity, as I've told you before. Okay, this entity is another, this geometry is another resource. Okay, which has a representation of our geospatial data as a WKT. What is this WKT? It's right here. You can see it. It's a point. Okay. So that was one parsing method to create RDF data. I can give you 5 minutes to follow along, and if you have any questions, feel free to ask. So we can move on to the next part of part 1. Do we have any questions so far? Did you get the GitHub repository? Okay. Yeah. Oh, the Wi-Fi is slow, okay. I see that we don't. Do we have any progress? Okay, has anyone managed to run the program? Download the library at least. Okay. Okay. So, because we are a bit tight on time, I will be moving on. Just know that all these files are uploaded on the part one of the tutorial. You can follow them along if you haven't had the chance to write them down and run them here. We also have the results uploaded for part one, so you can have anything from the GitHub link. I'll be moving on to the second part of part one, which is very, very similar in essence to what we did in the first part. We are going to be using another mapping faculty of the Topos KG library, but this one uses something that's called RML mappings. Okay, if you work or if you plan to work or if you're going to work anytime with RDF data, you're going to run into RML mappings. What is an RML mapping? It's a language basically. Okay, it's the RML mapping language, which is responsible for taking data sources like CSV, JSON files, etc., and creating a mapping for RDF data. Okay, it's a bit more specific. These are files that we can change, that we can edit to our liking. So, you know, we can have a bit more of an agency to the mappings that, to the RDF data that's going to be created. So what we're going to do here is build a very similar script to the first one, but instead of creating RDF data directly, we are going to create mappings first. We can edit these mappings, and after we see that these are okay, everything's fine, we will run the program again to create the RDF data from the mappings this time. Okay, so the file will be very similar to the first part of the tutorial. Okay, so far everything is the same. The only thing that I've added from the previous script is the generator. I've created a default mapping generator. What is this default mapping generator? It's a way to create a very basic RML mapping for our data. Okay, so we don't have to write it from scratch. Now, if we call this generator and give it as an input our JSON files, okay, it will create a mapping for its file. So, we provide the type of file that we're going to give to the generator, the input file, and the output file that's going to be our mapping files. Okay. If we run this script, this will create a mapping file that will have the extension TTL. It's a turtle. Okay. These are also RDF files that we haven't talked about. Don't worry too much about it. It's just a different syntax for our data. Okay. And you can see that this will be the kind of mappings that we'll get. Okay, that's what an RML mapping file looks like. It creates a map, let's see. Let's go down. Okay, so it creates a lot of maps. Okay, let's say when you find something that is inside the features, for example, of a JSON dictionary, say that it is a geometry, okay? And what will this geometry have? It will have this ID, this resource ID, and it will have a property, a predicate, that's called as WKT, okay, which will save this geometry that we've created from the JSON files. So if you see, these are mappings that exist for every object that appears in JSON files, and every property. For example, wiki link here is for points of interest. If you don't remember the files. Okay, so for example, this file had property types, type, which is point of interest, has name and the wiki link. Okay, these exist here as well in the mappings. Okay, and what this mapping says, when you find something that's called has wiki link, okay, map it onto something that we call ontology wikilink. Okay, that's our predicate. That's our column, for example, in an SQL database. Now, these mappings we can edit. For example, we can add to them explicitly that this class is point of interest. Okay, we can add that part here that says, okay, when you see and create this kind of object, also add a triple that denotes that this is part of a class. Okay. So, after we have our mappings, and I can leave you and give you some time to run them. After having our mappings, we can use again a method provided by the default mapping generator to create basically these triples. Okay, so as an input this time, it will not be the GeoJSON files themselves, it will be the mappings that we created, and the output will be an RDF graph. Okay, it will be an RDF file for each input file from the mappings. The script for that is ready, and it's called mapping to triples. So you can run okay. And right here, let me open this up a bit. The generator says that, okay, I found a file with 25 mappings and I generated 33K triples. Okay, this happens for each file, and the result again is n triple files, the extension NT, with the RDF data that we wanted to create for this part. So right now this concludes part one. And what we have as an output, what was the result of this part, is an RDF graph that we can upload in a triple store that we can query. Okay, I can give you 5 more minutes to try it and test it if you want to see how it works, and then we can move on to the second part. Again, if you have any questions, feel free to ask them. That's why we're here. Have we managed to generate mappings from these files? Yeah? Okay. Again, this part is also uploaded, so you can run it at home. Everything is there. The results are there. The files, the Python scripts are there. Because, again, we are running a bit tight on time, I will be moving on to part two. Part 2, as Despina said before, we will be loading the data that we created, these empty files, okay, into a GraphDB instance. Okay, what is GraphDB? GraphDB basically is a database management system for triple data. Okay, like Postgres is for the SQL, we will be using GraphDB for knowledge graphs. Okay, so you can go to part 2 of the tutorial. We will be deploying GraphDB with Docker. As you know, we usually do with databases. It's preferable to install them in a Docker file. If you have Docker, you don't need to follow the first instructions. These are just to install Docker on Ubuntu or on Windows. And what we need to do right now is to create inside this directory, inside part 2 of the project, we're going to create a directory named data. Okay, this is where we're going to move all the data that we created in the first part. Okay. Okay, so this command simply moves all the empty files into our data directory. Okay, and all we need to do right now to deploy the GraphDB is just run these 2 Docker commands. Okay, that's it. That's very simple. If anyone is familiar with Docker, that should be a very easy build to do. For those that don't manage to build the Docker, we also have some endpoints available on the README of the tutorial. You can access them. It's already a GraphDB instance. You can see it. You can do some queries there. Please try to install the Docker so we don't have too much traffic on these endpoints. Right now, the Docker is built. Okay. We can run a container. Okay. And this targets a localhost. Should be ready, okay. Okay, so this GraphDB instance is loaded. We can access it through our localhost. You can see here that this is our database. And we can go to the Sparkle endpoint, okay, to perform some queries. Okay, so a bit about Sparkle. Sparkle is very similar to SQL. Okay, it has a very similar syntax. You see that it's select, where, all the usuals, with limits, group bys, order bys. Okay, so what Sparkle does that SQL doesn't is it's basically some pattern matching on these triples. Okay, our data are triples. Subject, predicate, object. Okay, so when we want to search something using a Sparkle query, we want to specify a pattern that we need to find. These, for example, here are variables. What do we say in this query? Find a subject, a predicate, and an object. Basically, we say get everything you can from the database. Okay. With limit to 100, we just say find everything you can, and the limit to 100. So basically, just get the first 100 triples you find from the GraphDB instance. Okay, so if we run that, you can see here all the data that we collected from. You can see all the triples that we have stored in our database. Okay. You see here, these are the resource files, and these are the ontology files. If we click them, okay, if we click resource here, you can see the things that are stored in this resource. As I've said, these are URIs, so these are something that eventually we want to access on the internet. For example, here this resource shows that we have the resource here, and it has a predicate, which has geometry. Okay, this is the target object. It has a predicate, a property that's called type. This denotes the type of class, what type of table this is. So it's a river, okay? And it has a link to some property files, okay? Some properties from the initial JSON file. So, for the few minutes that we have, I'm going to show you just some very simple GeoSparkle queries. Okay, the first one we already ran. It's just a query to get 100 triples, that's all. Okay, again, all we need to do is just specify the pattern that we need to match. All the patterns are triples, okay? These are triples that we're talking about. So, for example, this query gives us 100 patterns. If we want to get 100 geometries, 100 the representations of the geometries as WKTs, okay, all we need to do is follow the second query. Okay, again, pattern matching. What will this query match? Subjects, that's a variable, okay, that have this predicate as a constant, so subject that have the geometry, okay. This geometry, again, is a variable. It can be anything we want. And this geometry will have WKT representations, okay, again, a variable. If we run this, you'll see that we'll get WKT geometries, okay. For example, this very big polygon, this is the polygon for Hamburg. It's our largest polygon here, okay. And for some more complex queries, we can get, for example, Sentinel-2 images that intersect with points of interest. That contain points of interest. Okay, so these are the Sentinel-2 images, okay. And we can access this, for example. This should have a thumbnail. Okay. This, for example, a Sentinel image that we collected from our dataset that shows one point of interest on the map. Okay. And our final query, which will be a bit slow. Okay. What this query does is it collects. You can see here, these are the GeoSparkle functions. Okay, these are functions that perform operations on WKTs. Okay, so these are just geospatial operations. And what we search with this query is Sentinel-1 images that intersect with rivers and with points of interest. Okay, and you can see that the query took about 20 seconds to run. If you are familiar with databases, that's because it's double join, basically. That should be a lot slower. Okay, that's about it. I'll leave you 5 minutes to try these things. You can access the endpoints to try the queries. These endpoints are on the README of the part 2. If you go here, you can access them. These are GraphDB instances. You can run some queries, try these things out, play a bit with Sparkle, and that should be it for my part of the tutorial. Again, I'll give you 5 minutes. If you have any questions, feel free to ask me. More than happy to answer. And Sergio should be taking over.
Hello, can you hear me? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, hello everyone from me too. I am Sergios Aneskefalidis. I cut Kostas' presentation short. Also, I am kind of loud, so I don't know if we should close the door because we will annoy them. So I will start my stand-up bit now. The tutorial is over. No, that's a joke. It did not register. Okay, so why are we here? That's a good question. We had some data. Knowledge graphs are great at integrating heterogeneous data. That's why we use them. That's why we love them. And okay, so we have these images. We have the geometry of Hamburg. We have some points of interest. So we have this like a toy knowledge graph, right? And this toy data. So just to spell the data, some images, okay. The goal in the end is to do something useful with them, right? Okay, so we parse them, we put them in a knowledge graph, we create a knowledge graph out of them basically, and then we put them on GraphDB. Okay, great. Now that we have them in GraphDB, we can query them. That is nice, that's great. So if somebody knows Sparkle, and he also knows our knowledge graph or ontology, and if our knowledge graph was a bit bigger or a lot bigger or like super massive, like the one that we used in the European Space Agency project that I will be presenting tomorrow, we could run some interesting queries like, okay, I want to write a query that gives me images of rivers taken in 2022, and these images have less than 10% cloud coverage, more than 50% vegetation coverage, and I also want these villages to include villages in them, and these villages to be in Germany. Okay, so that's an interesting query. Somebody might need to write something like that to do some kind of analysis on this satellite image data. But again, that's complex. So you saw the queries that Kostas showed you. They were kind of complex. I don't know how many people are familiar with Sparkle here. Okay, you are my target market here. Okay, so I'm working for you. So the idea here is that, okay, not a lot of people know Sparkle. So what if we could just write natural language requests and then get a result? So just throw Sparkle out of the equation. We don't care about Sparkle anymore. We just write in natural language, like we do in ChatGPT and Gemini and all these kinds of stuff, and we just get the images that we like. So this is what question answering is, and we start with a small presentation, and we will go to the demonstration part on the next part after the coffee break. So question answering is the computer science discipline of understanding and responding to questions made in natural language. Now that we have ChatGPT and Gemini and DeepSeek and all these kinds of stuff, that's what we do the entire day, right? You're like, okay, I want this, answer that. Okay, I want this, and the model answers. These kinds of models hold their knowledge in their model weights. This is great because they can reason about the world, they know a lot of stuff, but they also don't know a lot of stuff and make a lot of mistakes, right? So you have used ChatGPT and it has said something that's like, yes, Greece has 10 million people, and then it ends up saying, no, it actually has 2 million people. So they get confused, they are incorrect, they do not have access to our knowledge graph, right? So I build this knowledge graph here, I cannot ask ChatGPT to answer over it, I cannot say, give me 10 Sentinel-2 images with like villages, I cannot do that, right? So here comes knowledge graph question answering. So knowledge graph question answering is the task of, again, question answering, but this time over knowledge graphs. So we have a knowledge graph as our information source. The goal here is to increase accessibility to knowledge graphs. So if you don't know Sparkle, you can interact with a knowledge graph without needing to learn Sparkle. And it's also useful for AI systems, for AI agents. Why is that? Well, nowadays, multi-agent systems are all the rage, and these systems need to interact with each other, right? So what we can do is create a knowledge graph that holds information about the system, hold information about the different agents of the system, and have all of these interact with each other through this knowledge graph. So we have this semantic web of this is to close the wall. Okay, so we have this like semantic middleware among our agents, and then we use it to help them communicate. Now, there are two main approaches to knowledge graph question answering. The first one being semantic parsing, where you translate the natural language question to Sparkle. The second one is information retrieval and graph reasoning, where you essentially have the model go through the graph and try to understand what is happening there. Now, geospatial question answering is a specific kind of question answering where we care about quantitative or qualitative geospatial knowledge. So if my question needs geospatial knowledge to be answered, so meaning that we have like which states does the Mary River cross, or what is the distance between Brisbane and Sydney. In this case, we have a geospatial question answering question. Okay, so geospatial knowledge, as we saw, is either presented either as coordinate pairs or detailed geometries. They can be points, lines, polygons. Well, these are the types of representations. And here comes our first system. So TerraQ. TerraQ is a question answering system. It's a spatiotemporal question answering engine targeting satellite image archives, and it was built for the precursor demonstrator digital assistant for digital twin Earth project funded by the European Space Agency. And it's supposed to tackle requests like the following. So find 10 images of Piedmont with cloud coverage under 20% and more than 50% vegetation coverage taken in August 2022. So what we usually do is that we have these graphical user interfaces that gives us access to these satellite image archives, right? So because we have like millions upon millions of satellite images and so much data, we have this user interface where you just select a box which is your area of querying, and then through various like graphical elements, you say, okay, I want vegetation over 50%, and cloud coverage less than 20%, and I want the time rates to be like that. Okay, so we do that, we already have that, that's great, that has been working, but as we build more intelligent systems, we want more capabilities. We don't just want to do this like GUI stuff. Here we can express questions that we cannot express in existing systems. Why can't we express them? Because, okay, say that you want images from, like one image from every single village in Europe. Like not every single village, no, I will make something a bit better. Like every village in Europe that is less than 1 kilometer away from a river. Like how can you like select it? How can you define that? You can't define that. So that is why we need like these query languages like SQL and Sparkle, because we want more complex queries, and because we don't want to write these complex queries, we have tools like TerraQ. So TerraQ follows a semantic parsing paradigm. It translates natural language into Sparkle, and then we execute the Sparkle query over GraphDB. Any RDF store really, but we use GraphDB because we like it. So it's implemented as a component pipeline, and it uses a combination of modern classical natural language processing techniques to ensure responsiveness. Because this was a digital assistant project, we cared a lot about actually being able to answer questions reasonably quickly, right? So if you ask me something and I answer in 5 minutes, well, that's not that great. You want your answer in 1 second, 2 seconds, 3 seconds. You can say, okay, it's like 400 gigabytes of data, so I can wait for a few seconds more. But again, you want your assets to be fast. I will also, okay, this was presented in IGARS in August, the system. And like what we will keep here is we have 4 conceptual steps. The first step is the one where we do entity linking. What does this mean? This means that we go to our natural language question, this one over here, and you see the colored words. So the colored words and phrases are the parts of the natural language question that can be mapped to the knowledge graph. So, for example, Piedmont. There is a node in a knowledge graph that refers to Piedmont. Or cloud coverage, or vegetation coverage. There are like edges in the knowledge graph that refer to these things. So for our model to be able to create this query, it first needs to understand which parts of the knowledge graph it needs to access and which parts of the knowledge graph will be useful to create this query. Okay, so this happens right here, and then the rest of the other parts are for actually generating the query. So question answering is generally split into 2 phases. The first one, entity linking, where we see which parts of the knowledge graph are relevant to our question. And the second phase is query generation, where we just generate our query. And now we have a demo, so exciting stuff here. We are getting visual. Let me click this and use one hand to navigate it. Luckily, I was prepared for this. So this essentially is an application like the one that we want to create, right? So this uses all the technologies that we are showing you today. It uses a parsing library, it uses GraphDB, it uses TerraQ, so a question answering engine, and Leaflet to actually generate the map. So I will click suggestion here. So I have the question, find Sentinel-2 images in France with cloud coverage less than 10% acquired after March 2020. Okay. And here you have it. Okay, so I had this natural language question. You now can see it right here. I requested 10 images, and these are my 10 images. So images of France. If you can see also, you can also see them here. The image is demonstrated. You can download them. You can click them and see metadata. This does not have all that much metadata. That's the idea. So that's what we want to do. Okay, serious. So since you have this tool ready and actually working, then what else do you need to do? It's over, right? No, it's not over, because TerraQ and what we have been doing in the community for a while is that we create specialized question answering systems. We create systems that are made for a specific knowledge graph. And because knowledge graphs are very different, because I have different data and different representation models and different ontologies, then we have the problem of, okay, your system does not work for my knowledge graph, and I cannot easily transfer your question answering engine to my knowledge graph, so I need to start from the beginning. So I need a question answering expert to create this system, or some person to actually do these things. Like, even if I have technical knowledge, of course you have programmers, you have software engineers, we have technical knowledge, but you might not have the person that is actually knowledgeable in these things to create this system. And it's also a lot of duplicated human effort, right? Even if you have the knowledge, you need to do it again and again and again. So here comes Pythia. Pythia is a knowledge graph agnostic question answering engine. It requires minimal setup and no modifications. So you just plug it into your knowledge graph, you give it your knowledge graph, and then you can answer questions over it. There is no need to actually go in there and change anything, or like, worry at all about this kind of stuff. So it combines knowledge graph exploration with semantic parsing. It consists of LLM-based components. I will not bother you with the architecture too much. Some things are similar to TerraQ, but you see less steps overall, all of them LLM-based, and this allows us to do this reasoning over any knowledge graph to be able to answer questions over any knowledge graph. So one of the most exciting functions of Pythia is that even though it's generic and universal, it has achieved state-of-the-art performance in standard question answering datasets, and like DPpedia, Wikidata, and even specialized knowledge graphs. Now, the motivation, as I told you previously, is that we have been building question answering engines for a while, the first one being in 2018, and every time that we need to build a new one for a different knowledge graph, it was like a lot of effort and a lot of pain, and we did not want to do this anymore. We want to have a solution that is just plug and play and it works over any knowledge graph. Now, as I said previously, no modifications, no training data required. That's also a problem that you might have. So you have a project, but your project does not have data before the project runs. So first it's like chicken or egg, what came first? Because if I deploy my project and users use my project, I can gather data, I can then train better models and do these kinds of stuff. But if my models require data to function, then how can I deploy my project? So it requires no training data, but can take advantage of data as you collect them through like the lifetime of your project to actually improve its performance. High accuracy, as I said previously, and of course, open code, open data, so you can go in and do whatever you like. And now, the setup steps for Pythia are the following. Okay, this is like part 1 and 2. We have our knowledge graph. We load it into an RDF store. So, okay, we need an endpoint that has our knowledge graph loaded, stored, that we can start to query. The second step is that we need to learn some very basic information about our knowledge graph. We cannot be completely like oblivious as to what our knowledge graph, how our knowledge graph is structured. We need to know which edges of our knowledge graph give names to our URIs. So for example, let's say that in my knowledge graph, like or here, Hamburg is represented as 8D15, 6, 8, 7, 16, 17, has 3, 4, 5, 6, 0. Okay, if somebody reads that, he cannot understand that this is Hamburg, right? You're like, okay, that's just magic pizza, I guess. So there is a label that actually says, okay, I start from this node, and using this predicate, this label predicate, oh, this is Hamburg. So somewhere in the knowledge graph, there is a connection that connects this node to its actual name. So we need to know which paths give us these names for every single one of our nodes. It's usually a single path for every knowledge graph, so we just need to know that and be able to input that to Pythia. Likewise for descriptions, but this is an optional feature to actually improve performance. Your knowledge graph might have description data like Wikidata does. And of course, there's various other types of information you can give. There are various other types of information that you can give it to improve its performance. So the setup steps are, we download Pythia, we do indexing. So indexing is almost automatic. It requires these kinds of input, right? So it has a bit of human effort. Then Pythia essentially learns our knowledge graph and is ready to query it. We do some configuration, so give it an API key for our LLM provider of choice, give it the endpoint address for our GraphDB or Virtuoso or whatever RDF store we use, and then we can also give it some better instructions to align with our expectations. If we go back to our demo here, you will notice, is there any example of that? Oh no, for the first time. Okay, no. I want something else. Come on. Okay, this might be good. Okay, so you can see here that there are a lot of images that do not actually only show Belgium, right? So 2 and 1, like 50% Belgium, 50% France, right? France is here, right? Yeah, okay. So 50% Belgium, 50% France. What we do here, for example, is that when we say I want images of something, we do intersections. So I want these two things, the geometries, the polygons of these two things, to intersect. You could say, why, serious? It would be better to say containment. So, okay, if I want an image of Athens, I want Athens to be contained, not just intersect my image. Well, this is kind of a trade-off, right? So, depending on what images you have, you might, for some places, they might be too large, so you will never get an image of that place, or there might be not enough images in each particular location. So these intersections essentially are kind of a balancing act to make sure that we always get something and that we always see something that is relevant. So here is Belgium, it intersects with these polygons. So these are the polygons of our images essentially. So okay, these are the images that are returned. Pythia by default would not do that. Like Pythia is not built for this application specifically, it's just a general engine. So to better align that with our expectation of using intersections, we can just say so. We can input it a bit of text and say, okay, I want you to use intersections for these kinds of stuff. And so it aligns with what we expect from it. And after that, we are just ready to go ahead and use either a computer line interface or use it through an API endpoint to run our stuff. 10:30 exactly, so it's coffee break time. And when you come back, and I hope that I teased you enough to come back, we will be going into Pythia and seeing it run live. Thank you. 1, 2, 3, 4, 5, 6, 7. Oh, you can hear me now. Okay. After eating and I've taken our coffee, it's time to proceed. So, can I do this? Oh, yes. Ένα, δύο, τρία. It does not actually function all that well, but I kind of need my hands, so I will be here. So, welcome back to our tutorial. Now we are about to get hands-on with Pythia. So, let me close my emails. Yes, great. And we all go to the tutorial page, and we are on the part 3 of the tutorial. First of all, this page links to the Pythia repository. As I also wrote in the email that I sent you, Pythia is actually in the very early stages of development. This is not even version 0.1, but it's improving rapidly. It's a project that we are using. It's a piece of software that we are using in multiple projects, and we are interested in integrating it into even more projects. So we are spending a lot of time working on this. The problem with not being even in a public release version yet, but the paper is under review, well, the problem is that the repository is kind of is not great. I tried my best to make it workable for the tutorial and make the code readable if you are interested in taking a look, and also it does not have a particularly good documentation, so the tutorial is actually the best documentation that you can find on it right now. I will tell you more about our plans for that for the future after we are done with the hands-on part. Okay, we are linked to the repository. We can ignore that for now. The first part of the tutorial here is downloading Pythia and its dependencies. The problem with that is that the Wi-Fi is pretty slow, as we have all noticed, I believe. And it also disconnected, but reconnect, okay. So the Wi-Fi is pretty slow, and it needs a lot of Python libraries to work, actually. So I will not be downloading it from this, I will not be loading it right now, but if you follow the instructions, I have checked them out multiple times, and they work. So the setup instructions are okay. If you follow them as they are shown to you, it will function just great. But I will go to another a version that I prepared earlier. So, and also I forgot something to send you. Okay. So we can do this in two ways. I don't know if you want to follow along or if you would prefer to just focus on seeing what's happening here. I would think that following along has not had a lot of success until yet. I have prepared like an API key and endpoints that you can utilize while we are doing this, but if it doesn't, if we are not interested in following along, and oh no, I can't connect to my computer for some reason. Okay, can I connect to this computer? Everything is going terribly wrong. Okay, let's try to connect through our phone. So yeah, let's not do the follow along part. The instructions are there, the instructions work. If you are interested in revisiting what we have shown you, you can do so at your own pace. I will now try to connect to my phone to connect to our servers. Otherwise, this will be a bit unfortunate. Let's hope for the best. Please. SSH. Oh, okay. Just give it a couple of seconds, I guess. If that doesn't work, well, we will need to try to download Pythia here, and it might take a while. Yay. We are in. Okay, it looks like Greece is too far from Latvia to actually have quick response times around here, or more likely something is going on in our university right now with the network. please don't DDoS me after seeing my server, my work computer. Okay, so we are in. Okay, I will balance the microphone in front of me, and oh, it's extremely slow, but it's okay. No problems at all. So we begin by cloning Pythia. Okay, that works great. Then we create the code environment. Can you see these two things? I will make them a bit larger. Okay. Can you see them now? You can probably see them. Okay, so we create the code environment. This essentially is how we manage all the dependencies of Pythia. So instead of needing to install 100 different packages by hand, we just run this one command on Linux and it just works. Okay, then we activate the code environment and I will start with the activation. Oh my God, the typing speed. I am seeing in the future and guessing that I have written the correct thing. Yes, I have. Okay, so it will be a bit cumbersome, but please bear with me. Don't judge me too hard. I tried my best. So, okay, we have activated our environment and everything is great right now. So we enter the folder of Pythia. Here I have it with, I don't have capitalized the first letter. And if we have created our environment correctly and activated our environment correctly, and we are in the folder of Pythia, we should be able to check that everything functions by running the command that you see here. So Python, pythia.py, and version. I have already written the command and we are waiting for it to actually be sent. It's like my server is in another planet. Oh, what? No. Yes, okay. Is it dead? That's it. Yeah, okay. So we need to do something else. Give me sign into Wi-Fi network. Yes, it's over the screen, right? Yeah. So, okay. This is dead probably. This takes around half a second to respond, so I don't know why it's not responding at all. This is what happens in live shows. You can expect that. Unfortunate. Okay. Okay. Be fast. Okay. This has responded. This has not responded. I put the password incorrectly, which is interesting. Do I not know my password yet? Okay, we are once again in, and it looks like I need to be quite fast actually for it to function. Well, if it continues being like that for a few more minutes, I will just show you the output here. I have already added that, so that is something at least for all of us to see. Yeah, okay. I can start, I guess, trying to build Pythia locally and see if it's okay. That is very unfortunate. Okay. And let's also do a speed test. Oh, no, it's my internet, it's extremely slow. So, okay, my phone is not better than the Wi-Fi that you already have, so okay. Okay. Please. Okay. Okay. Does it work now? It might.
Έχεις πρόσβαση στον drone.
Σε ποιο?
Στο drone.
Όχι, αλλά τώρα δουλεύει. Now it seems like it's working, so I am very glad that this is the case. Finally we are able to write in real time. Okay. So now please forgive us for this small inconvenience. Okay, now we have activated our environment, we are in the Pythia folder, and now we should be able to just see that Pythia functions well by just running this command to show us its version. Okay, everything is great. So, Pythia has been set up. So if you're following these instructions later, you should be seeing the copyright information. And as our next step, as we saw in our slides, okay, no slides. So here, we download Pythia, we install it, but there is no installation right now. We just download the source code, and then we do the indexing part. Okay, to do the indexing part, we first need to compile a Java program which is used to extract the nodes from our knowledge graph source files. Why we need that? We need that so that Pythia knows what an entity is and what a class is from our knowledge graph without us explicitly giving it to it. We run this command just like it is, and it will just go to the correct folder and build this package. Now that we have also done that, we are ready to actually start the indexing process for Pythia. Now, as you will be able to see here, if I write the help command, as you can see, Pythia currently only has a computer line interface. The goal, of course, is to command line interface. The goal, of course, would be to actually create a graphical user interface for all this, but at the current stage, we are here. So as you can see, there are multiple commands. There are help pages for every single command, and we are interested in the indexing command. The indexing command, I can also show you that, has a lot of options. These are the configurations options that I told about previously. These configuration options that you will see here can be used to really be explicit about what we want from our knowledge graph, like our indexes of our knowledge graph to be. So this is essentially the learning part that Pythia does. And we might tell it where the labels are, the descriptions. We might want to filter specific classes, or might want to keep classes that have specific prefixes. Essentially, these are just options that are given to us to not have to process our files really a lot to be able to give them to Pythia for it to function. We can just use this to do whatever we might need for indexing. But because our knowledge graph is very simple, we don't actually have to do much in this case. What we have to do is, first of all, pass it the directory of our source files. So in this case, the directory of my source files is, I believe, bits.kg7. These are the iterations that I needed to do until I got the demo to work for this. So we had some problems making the correct knowledge graph. Yes. We first of all passed the source files of our knowledge graph. So if I go now, I will open a second connection, and I will probably pay for it with my life, but let's try. Okay. So if I go to bits.kg, and you see here, you see all the files that Kostas created in the first section. So the Hamburg.nt, Hamburg points of interest.nt, Hamburg rivers.nt, and so on and so forth. And as Despina told you, all of these are just good old RDF files, and you can see here the triples. So we have this entity, and this entity has vertical horizontal. Yes, it's true. So this Sentinel-1 image uses vertical horizontal V8s. Then we, for example, we have here this Sentinel image uses processing level 1, while this Sentinel image has processing level 0, and so on and so forth. So these are just our source files that we loaded to GraphDB. Now, we pass that, and we also pass it the label paths that I was talking about. So as you can see, not from this file, but let's open the Hamburg file. Okay, which one is it? It's Hamburg.nt. This is the source file that contains Hamburg. Okay, Hamburg is this thing right here, let's say. So, it's not actually this thing right here. Hamburg is this entity right here. So, Hamburg is ai-team-uoa.github.io blah 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 resource 54645 AC715 etc etc. If I give that to my engine, it cannot understand what it is. It does not understand that this is Hamburg, right? I couldn't do it, so an LLM can do it. So what we need here to do, and we know that because we constructed our knowledge graph in the first steps, is to find, okay, so how can I find Hamburg here? So I could even do that through a GraphDB endpoint, actually, but now I just skip it. Okay, so the correct part, the correct path is actually this one right here. So first of all, you use the properties link predicate, and after that, you use the has-gadm name predicate, or the has-name predicate. So this is just explaining that, okay, if you are on a node, to find the name of this node, you first use the first predicate, then you use the second predicate. If that does not lead you to a name, try the second combination. You use this predicate right here, which is the predicate, this predicate right here, and then you use this predicate right here. So we're just hopping around our knowledge graph to find the names of all these things. If I go to my source files, I can see that if I use, where is it, like, wherever it is, if I use has properties link, then I go to another node. From that node, if I use the has name predicate, which is right here, has name, I go to Hamburg. So I have found my label. We could build a system that does that automatically by essentially just searching on the knowledge graph. That is very straightforward to do. The problem with that is that essentially for something that you only need to do once, you only need to find this once. So you build your knowledge graph, you find this information, you just set it, never have to do it again. You would just have your LLM like search for it a bunch of time and just waste a bunch of tokens for something that is relatively straightforward. Especially if you're building your own knowledge graphs. The other option that we use, which we could just skip, is -t. -t says that we only want to use one computational thread. We could just delete that, but I have it just to not spend too much CPU time here. And we also use the filter option. The filter option essentially says to Pythia that I don't want you to include any nodes that don't have labels. So you use these label paths, and if you find a node that does not have a label, I don't want you to include it. Why is that? Well, a lot of times you have these intermediates. So again, in our Hamburg file, this right here is an intermediate. So this one is Hamburg, and Hamburg uses the properties link property and links to an ontology node, like a node of the ontology, class of the ontology, which just like combines all the properties of Hamburg that contains all the properties of Hamburg. It does not have like a manifestation in the real world. So I don't want my question answering engine to actually be bothered with that or incorrectly think that this is something that it isn't. I don't want to be confused. So I can just simplify the indices by saying, okay, whatever does not have a label, whatever you cannot read, just throw it away, we don't care about that. Okay, so these are our options. And okay, we press, okay, let's go, let's index this. And now what's happening, first of all, we extract all the nodes from our knowledge graph. This is a node, this is a node, this is a node, this is a node. We find the labels for all of these. So the label for this node is Wanze, the label for this node is Kühlbrand, this one is Süderelbe, etc., etc. Sorry for any Germans in the stands. After we have extracted the entities, and as you see, I just pressed a command, everything happened automatically, I didn't do much. Then a BM25 index is built, a FICE index is built, another index is built, etc., etc., etc. Now what happens is that Pythia asks us, okay, does your knowledge graph contain URIs with non-descriptive IDs? Yes, our knowledge graph contains URIs with non-descriptive IDs. As we saw, Hamburg is really just arcane stuff. So we say, yes, it does contain non-descriptive IDs. And now Pythia prompts us, okay, please provide Pythia with one or more predicate URIs that can be used to fetch labels. So essentially what I was explaining just now. And you could say, Sergius, why don't you change it to do it automatically? Well, I will, sorry, it's a issue. So I can just paste the labels that I had gotten previously. I paste them here, the same labels, just the same labels. So what does it say here? Okay, I build my indexes, but I might want to use the URIs not from the indexes for my internal logic. Please give me the same labels that you used to create the indices. Okay? Or at least in most cases you want the same labels. In some cases you might not want the same labels. Now the index is ready. Does your knowledge graph contain geospatial data with WKT literals? Yes, our knowledge graph contains geospatial data. Yes, we use WKT literals, and we just say yes. And then it asks us to say, okay, how do you represent WKTs? Like, again, what are the predicates that lead to these WKTs? We use the default OGC grammar, so everything is done, and we are ready. At this point, Pythia has learned our knowledge graph. Okay, let me close these things and scroll both to the bottom a bit. All right, now at this point, as I said, we know our knowledge graph, but we also need to configure some stuff. First of all, we need an API key because we are using LLMs and we want to have our LLMs be able to do stuff. One way to do that would be to actually pass this API key every time that we run our application. We can do just that. So as you can see, one of the settings is the LLM provider. We use OpenAI by default. The LLM model, we use GPT 4.1 mini by default because it's cost effective. And the LLM API key. If you're using a provider that is not like, if you're using a provider, essentially, you need to also pass your API key for it. What you can also do is you can actually open and sorry that I'm running this all through the terminal, but what can I do? You can also pass it an API key in the configuration menu. So, okay, I have already passed an API key previously. If you are doing this at home, you need to pass your own API key either through the command line arguments or in the configuration YAML. Here on the sorry, yes?
For example, we have LLM, we are LLM provider, like we host LLMs in Cloudflare.
Yes.
Our API is compatible with OpenAI API.
Yes.
Can we change endpoint to our endpoint and call,
Yeah, I understand. That is actually a very good feature that I don't have. So yes, I will make sure to add that. Right. So just make an issue like do that. I will talk about community engagement later. So let's keep that in mind. Thank you very much. Okay. Let's say that we configured everything. Again, we need to add our endpoint. Okay, which endpoint do you want to use? Let's use this one. This is my own secret super personal endpoint that I'm showing you right now. Please don't DDoS me. Okay, so again, I can either pass that every time in my command line arguments, or I can just pass it here through the URL. Put the URL in the configuration file. Then if our endpoint uses default HTTP security, we also need to use the username and the password. We might have our endpoint open. You should not have your endpoint open, of course, because then people will connect to it and mess it up. So again, we can either pass the username and password every time through the command line interface, or just set it in the configuration YAML. Okay, all of this is great. We have set up and configured our engine. Now, for the last part, before we start actually asking questions, we want to better align Pythia with our expectations. So this is what I was talking about previously. So we want intersections for our geospatial calculations, because somebody else might want a specific geospatial relation for specific cases. So I might say, if I want lakes, I want you to use containment. So lakes, I don't want intersection, I don't want overlaps, I want just containment. This is a way for you to configure Pythia without actually messing with its source code. Of course, it's open, and it's not that difficult to edit the prompts, because the prompts are also right there for you to edit. So we run this command. So Pythia configure custom instruction. And this is my custom instruction. So my knowledge graph contains satellite images. Satellite images cover very large areas. When I say that I want an image of some place, I want you to use, I want to use an intersection. And as I said, I am just using that as the user, right? I'm not doing that as the developer of the tool. The tool by default does not have this file is completely empty. You as the user can go in, just change it and align it to your expectations. So I'm going to use intersection unless I specifically say otherwise. For example, images of Athens give me images that intersect with Athens. If I say images that contain Athens, then show me images that fully contain Athens. Okay, and we save our file, and everything is great. I have everything, as you can see, in the README, so you can follow along at home. Every action that I take is written down here. Now, if you have not used NLTK, which is a library that Pythia uses, at this point, like before we proceed, it will start crying about stuff. It will say, I want this package, I want this package, I want this package, which is annoying. So the best way to just install everything and be done with NLTK forever is to just run these 3 commands one after the other. Be careful when you're copying my commands here, don't include this. I have added this to show that we are in the terminal. We must not include this like larger than symbol. Okay, I have used NLTK previously on this computer, so I have already downloaded everything, and now we are ready to run Pythia. Okay. Again, Pythia, Python, pythia.py. If you don't know I of course know what the interface is, and I have also prepared a tutorial, but if you do not know what the interface is, again, there are help menus for every command, pretty detailed, and explain stuff. Okay, so I want to run Pythia, py, CLI. Okay, so let's see. CLI. So this is essentially, okay, run Pythia through the command line interface. The other option to run Pythia as with a fast API server. Okay, lots of extraction again, but the basic ones are these down here. You must, okay, they not filled that well, but okay. You must give it an option, a selection of a knowledge graph. Pythia has a bunch of knowledge graphs pre-built essentially. Why are these pre-built? These are pre-built because they are used during the evaluation of the model. So we include custom dataset loaders and custom classes to handle knowledge graphs, so we can run our evaluation scripts in a very nice manner and that they're also reproducible. When we add, and you also can do that, so you can just go to the source code, add a new dataset loader, add a new knowledge graph. The code is, I would pat myself on the back and say pretty well engineered. But with it, if we are adding something as a user, just don't want anything to do with modifying the code, we use the custom option here. So we have our custom knowledge graph. Okay, so we need to add our custom knowledge graph. Oh, no, don't start, sorry. And then after the custom option, we also want to go to the, is this the wrong one? Yes, this is the wrong one. Go to Pythia, and we want to go to the indices folder. This folder right here. This is where Pythia has saved its knowledge of our new knowledge graph. And if we go here, we see all the indices that Pythia has created. It essentially takes the name of the folder that we gave it to create a folder with all the information for the index. So my newly created index is this right here, September 30th, time 11:32. So I'll just copy that. Or I don't have to go there, I can just remember the name of the folder that I gave it. And I say here, okay, I will also put my endpoint URL because I have not added my endpoint URL to the configuration.yaml file. If I had, I would not need to do this, but I have not. Okay, and let's begin. Let's pray that everything works out okay. As I said in the email, don't be mad at me if it doesn't work. And now it has loaded the indices, it has loaded its models, and we are ready to ask a question. And let's try our pre-canned questions. So the original idea was that we wanted people to be able to quickly load the knowledge graph and actually run stuff. So we created a very small knowledge graph, which has, it's a toy essentially. You cannot ask much, like it has one city and a few images and like a few points of interest, but like we can try our best. So let's say give me 5 Sentinel-2 images. So remember, here the magical thing that you might not like appreciate, but if you think about it, it is kind of impressive. We did not explain to Pythia the structure of our knowledge graph. We did not say how to create queries. We did not do much. We just wrote 4 lines of natural language text. So we want intersections instead of anything else. And then we said, okay, these are the configuration, go crazy on it. Now, it has identified Sentinel-2, has identified that, yes, so it has found the class Sentinel-2 from the, sorry, how do you call it? Oh, what have I done? Is everything okay? Ah, why are we slow? We are searching for stuff here. I don't know what we are searching for. The LLM probably got confused. This is what happens in live environments. I have never seen this before. Did I crash? Please? No. Is it running? Is my endpoint okay? Who is not okay? Pythia does not look to be doing much. Live bug fixing session. Okay. So my GraphDB endpoint is the problem here. So yeah. I have probably added too many endpoints on the same machine. Can we please go there and cancel this? Yes, please cancel, please. And I have also probably forgot to do something, so give me one moment here. Because, yeah, okay. I'm not using the default configuration. Let me change that back to the defaults. Sorry. I will explain the problem if everything works. If it doesn't, I cannot explain much. Okay. Let's try this one more time. Give me 5 Sentinel-2 images. Okay. Please work this time. Okay, let's see. Have we found the class? Yes, we have found multiple classes, but will we filter the correct class? Yes, we have filtered the correct class. Okay, know the special relations. Great. Yes, and the exploration part. Will it hurt us again? Has got name. What are you searching for? I don't know what you're doing here. Sorry. Did I? It was more impressive while it was working, to be frank. And I have no idea. I might have an idea. And you can, I woke up at 7 a.m. to test that it works, and it worked. So yeah, that's brand new for me. Oh, oof, yeah. Yeah, like, nah, I have, like, if I just check out, okay, it just gets stuck to the Sparkle endpoint. So what if we just change the Sparkle endpoint? It might work like that. Yeah, I probably did open too many endpoints on the same machine, and my GraphDB might be complaining. Okay, so can I open one of the Docker endpoints? Okay, let's see if it works. But this has there are different things. Okay. Does it have the data? It has the data. Great. Okay. Let's go one last try. So we are user. We are 1, 2, 3, 4. And now we give it our endpoint here. And we hope for the best. We will delete this and run this. And okay, I can also, let's check it out this time. I see. Filtering, planning, exploring. This is where we get stuck usually, isn't it? Are we getting stuck or not? Let's see. Let's give it a few seconds. Oh, yay, we got unstuck. Yes, it was the fault of the endpoint. Yay, I'm so happy. So, okay, I don't know what happened, but Pythia was not at fault. I'm not at fault. This was the most terrible 5 minutes of my life, probably. So, now, what happened there was that I have opened 6 GraphDB endpoints, and GraphDB might not be happy with that because you are supposed to pay 6 different licenses for that. But I tried to open them on the same computer for the demonstration purposes, just so you can play around, but now it works. So we got in the Docker, everything works fine. So these are the 5 images. We wanted 5 images. We can take a look at the query. So okay, what does the query say? It says, I have the Sentinel-2 image type, image. So these images are of type Sentinel-2. So these are indeed 5 Sentinel-2 images. Now, let's go to our next query, now that everything functions. And the next query is, give me 5 Sentinel-2 images of Hamburg. So let's make it a bit more complex, just a little bit. And if it works now, we'll also explain what the output here is. Okay, please work. Now I have lost faith in my software. I cannot look. Knowledge Graph Explorer. Is it a moment that everything goes wrong? Let's wait. It needs around 10. Oh, yay. Boom. Once again, I believe that we will win if the query is correct, though. Let's see if the query is correct. I'm using GPT 4.1 mini or GPT 5.1 mini. Oh, yay. Is it correct, the query? Yeah. OK. So let me walk you through what actually happens here. OK. So first of all, we are saying, and see how many things happen without you actually programming anything. So that's gonna be impressive. So give me 5 Sentinel-2 images of Hamburg. Okay, so first of all, Pythia says I need to run named entity recognition disambiguation. What does it mean? It means that I want to find named entities. A named entity is Serios, or Despina, or Athens, or Greece. So things that are very specific things. So here, mistakenly, it says that Sentinel-2, well, Sentinel-2 is a named entity, right? Sentinel-2 is a specific thing, is a specific satellite, right? But in my question, I want Sentinel-2 images. I don't really care about the Sentinel-2 satellite or anything like that. So, and it also finds Hamburg. Okay, so it says disambiguating entity Sentinel-2. It cannot disambiguate Sentinel-2 to anything. It understands, okay, my knowledge graph, my indices, I don't want that. So I disambiguate that to nothing. So that does not exist for me. Disambiguating entity Hamburg 2, and now this is the knowledge graph entity for Hamburg. And we also add this little Hamburg label here. So this does not exist in the knowledge graph originally, but we add that so the LLM can actually read and reason about this string. We will then remove it to be able to actually run the query on our knowledge graph. Okay, named entity recognition is done. Now we go to classes. So, okay, let's retrieve some classes from the knowledge graph. We have points of interest, river, Sentinel-2. Okay, Sentinel-2 is actually the relevant one. Okay, filtering the classes, and we have filtered nothing this time. Okay, filtering failed. It says that everything can be useful. Okay, that's actually a good thing to talk about later. After this is done, we create, well, actually, first of all, we try to identify geospatial relations. So the georelation identifier here takes the class and the entities and says, okay, I have a geospatial relation. I have a containment between Hamburg and Sentinel-2 images, essentially. So this Sentinel-2 refers to the class of images of Sentinel-2. Remember, though, that we said, okay, I don't want containments, I want intersections. Pythia would originally create Pythia, like GPT 4.1, which is behind all of this stuff, says, okay, this is a containment, but we don't want containments here, and we will change that later. So the software, with the instructions that we gave it, will take care of that later. Okay, then we also rewrite the question to remove the geospatial relation. This simplifies the next steps. So I have identified the geospatial relation. I do not need to actually care about geospatial relations anymore. So here we have, give me 5 images. So I just want 5 images, send them 2 images, whatever. Okay, here we create a plan. So we just want members of the Sentinel-2 class of things. Members of the Sentinel-2 class of things are the Sentinel-2 images. And in the end, we explore the knowledge graph. Okay, we don't have much to explore here. We know what the class is. We just need to write some Sparkle. And in the end, we produce our final Sparkle query. Notice here that we use geospatial intersection because it remembers that we want something different. So it changes this containment into an intersection. And we also have, like, we take the geometry of Hamburg, we take Sentinel-2 images and the geometries, and then we run this intersection here. And then we limit the output to 5. So we get 5 Sentinel-2 images of Hamburg. And now let's try one a bit more complex. So give me 5 Sentinel-2 images of Hamburg with less than 10% cloud coverage. Just like that, with this configuration, the default configuration, without modifying anything, Pythia has asked us questions over DBpedia, Wikidata, Yago, a Dungeons & Dragons specialized knowledge graph, a material science knowledge graph, and in all of those, it has achieved better than the state-of-the-art results of question answering. So it has managed to achieve better results than dedicated question answering engines built for these knowledge graphs. This is partly because of the architecture, partly because of actually making good use of the reasoning capabilities of LLMs. Here, okay, the query generator takes some time to think about stuff, and this is correct. Okay, again, we have our Hamburg edit geometry, images of Sentinel-2, image geometries, okay, link to properties and cloud coverage. So, okay, we have this medium probability cloud percentage, so this is our cloud coverage, and we say we want the cloud coverage to be less than 10%. Pythia goes in, sees the properties, understands that 10% is represented like that, intersection, and here are results. So again, we have a correct query and everything works fine. So this is the presentation part. I see that my colleagues are anxious about time, and I'm also anxious about time. Okay, because we spent some time here doing chasing our tails essentially. So I will be very fast. Now, let me show some little like table. Now I'm really proud that it works, and I would like to flex a bit more with more tables, but it's okay. So first of all, named entity linkers. Pythia is configurable, that's part of the point, customizable. So it supports multiple entity linkers, it supports, the entity linkers is the part that matches Athens to the knowledge graph node of Athens. It's this part, okay? The named entity recognition and disambiguation part. So Pythia supports multiple well-known entity linkers like Facebook's ELQ and Bella, which are actually state-of-the-art. What is an older one and introduces its own one, Pythia Nerd. So Pythia Nerd is generally applicable. As you saw, we did not need training data at any point. We didn't train anything. We just plugged and played. But it is slower. So as you saw, Pythia takes around 30 to 40 seconds to answer, which is actually, it's not terrible, but it's not great. It has a lot of optimization headroom, of course, because the code can be improved, the prompts can be improved, but any case, whatever happens, Pythia Nerd will be slower, it will need a few seconds to answer because it uses large language models, while ELQ and Bella use dedicated trained models to achieve their results. The actually surprising thing is that during our benchmarks, we noticed that Pythia's named entity recognition component and disambiguation managed to outperform on average both ELQ and Bella, and also was applicable or more knowledge graphs. Like the second we expected, but actually being able to outperform them, models that have been trained on specific datasets, was surprising to us. Next, for class linking, and this is the problem that we saw previously. So the problem that we see here, and it's actually way more obvious in larger knowledge graphs. So here I'm asking for Sentinel-2 images, right? Sentinel-2 images of Hamburg. And it gives me also the Sentinel-1 class and the River class. These are useless to me. And then it tries to filter them and actually fails here. So depending on the question, on the context, it might be able to filter some irrelevant classes out. The more classes you have, just like the more entities you have, the more false positives you have, the more complex it is for the model to reason about what is actually useful and what is useless, correct? What we have also developed, and so here what we are using is a technique called retrieve filter concept linking that we have developed. What it does is, okay, I have my indices, I query them, and then I try to filter out things that I don't need. An alternative to that is to create, and this is suitable for medium to large scale ontologies, because this technique, which is way better results-wise, cannot be easily applied to large ontologies. So for smaller ontologies, like ontologies with 10, 20, 30, 40, 50 classes, it is actually much better to utilize concept linking on descriptions. Essentially what it does is that, first of all, we pass it data and automatically creates descriptions for our classes. And then it utilizes these descriptions, it passes them as context to an LLM and utilizes these descriptions to understand which classes are relevant and which are not. This is better because it uses essentially some information about our knowledge graph that it does not like embedding similarity or textual similarity. It actually has gone in the knowledge graph, it has understood what every class represents, and then it uses reasoning to understand which of these classes are relevant to our task. And of course, we can also go in there and add the descriptions ourselves. So if we have a better understanding of what's happening, we can go in our model, and okay, I will close this so I can show you an example, I guess. So if I go to, do I have anything? Okay, for example, if I go here, these are the classes of this knowledge graph. Is a knowledge graph inspired by the Dungeons and Dragons pen and paper RPG. So these are the classes. I can go here, and because I know what the knowledge graph contains, I can write a comma and then write a description, like what is this? So this class refers to that. And when I have ambiguous classes, like we have in the Yago to Geo knowledge graph, for example, where we have OS counties, OSI county councils, OSI county and city council, you can go in there and really, by describing these things and explaining them to the model, it really improves performance by a lot. And you can see that here, seeing how concept linking descriptions manages to reach as high as 95% accuracy on some knowledge graphs, while the other technique is pretty much a lot lower. Now, the hands-on part was supposed to show you how we can create descriptions, but we don't have time. And I will leave that for the end, right? Yes? And real quick leaflet web development class right here. So, after we have created Pythia and everything is functioning really, really well, we want to create a little visualization like we did for, not this endpoint is the one that doesn't work. We want to create a little web application that visualizes results like the one that TerraQ has, right? So that was nice to look at. So this time, instead of opening Pythia as a command line interface, we open it as an endpoint. So an endpoint built using Fast API. Our endpoint has started at 1699 on this port. Okay, and now we will show you, I'll show you how we use, okay, I need to close this, close that. Why don't you have these things open? Okay, so I'll need to go here, and these are included, of course, in the sources. Okay, so I have these two little HTML files that use leaflet and let me show you how they actually function and how Leaflet functions. So of course this is not like a web dev tutorial, but we can take a look and see, like, we want to show you the entire pipeline and all the tooling that we use, so you have like a complete opinion. As you can see, we are not really, like, we have developed these tools to make stuff relatively straightforward. So if you have a technical background, these things are very straightforward. And that's what we were aiming to do. We did not want these things to be like magic and arcane and stuff like that. Okay, so this is my very basic web application. I will just go through this, which does not use the map visualizations, and then we can compare to the one that does use map visualization. Okay, so I have my header right here, then I have my input field. As you can see, my input field is just a little box right here and the button below this box. And okay, so this is all my input. Then I have a section for showing results in a textual format. And then I have my little JavaScript script right here. What this does is that it says, okay, check for empty input. If your input is not empty, you can proceed. Okay, now you have sent a request to Pythia. This request is sent right here. This is the address of the endpoint. Okay, send this request. When you retrieve this request, parse it and display it on the little text visualization thing. Okay, so let's try to see if it works. Oh, 1, 2, 3, 4, 5. Yeah, will it work? That's the question. Okay, we are filtering right now. Okay, and your relation identifier, and not the exploration planner, and planning, and exploring, and if it works now, we are all happy. Did it work? Is this the correct? No? Yes, okay. The query generator, and now we should expect to get 5 Sentinel-1 images right here. Any minute now. In a textual format, of course, it's not, we do not have the actual images here. Okay, so we get our results and everything is great. But it would be nice if we could have a little map visualization. So enter Leaflet. Leaflet is a JavaScript library, and the difference between a JavaScript library for creating layered maps. It's a very nice library. It's fairly high performance for considering that it is JavaScript, and it is very widely used. In the complete.html file, you see marked with these comments, like that, like this. I mark the parts that are different. So we have built a very basic application, and then we see exactly what is different here. So first of all, Leaflet requires its CSS style sheet to function. If you do not include that, and trust me, I failed previously, so yeah. You have some just arcane, instead of having little map, right here, which is beautiful, you have parts of the map all over the screen. It's just you think that somebody has gone very wrong with you. Okay, so first of all, we include this style sheet, and then we need to include an element of an HTML element that is ID as map and has a set height. These are two requirements, like the style sheet and this map element are the requirements for Leaflet to function at all. After we have done this, essentially this just says, okay, I want to place my map here and I want my map to be this big. After we have done this, we include these two JavaScript libraries, like Leaflet and well-known, which we will use to parse well-known text. Okay, we have included this, great. And now it's time to initialize Leaflet, the Leaflet map in our script. Leaflet essentially functions with this global object, this singleton, named L, probably from Leaflet, and we do everything through that. So L.map means, okay, I want you to create, like to say that, create a map on this HTML element. The HTML element is map div. Map div is this element right here. So we create our map, we sender its view in Hamburg, at least ChatGPT told me that these are the coordinates of Hamburg on a Leaflet map. And then we create the background, the tiles, essentially what we are seeing right here. Afterwards, we have a getWkt function, which goes against the WKT endpoint of Pythia. I created this to mirror how TerraQ functions. So essentially what happens is first we get our images from Pythia, from the Sparkle query, And then the front end says, okay, I want to get the WKT for this image, or I want to get the Sentinel-1 image for this image. Okay, this UI is not a generic, it's not plug and play, it's not anything. I'm just showing this to you to see how all of this fits together and how we made TerraQ and this application that you saw previously. And you can do something like that using Pythia or anything else. Then, okay, inside the main function where we send our request, what do? We clear all our layers every time before we add new layers. And then, for each single result, we say, give me your WKT. And then we use this singleton to parse the GeoJSON and add it to our, sorry, we parse the WKT here, and we use this, the leaflet global to say, okay, this is GeoJSON, and then I want you to add it to our map. And if we ask the same query here, it should actually display the geometries of 5 images right here. You can also display the images on the map, and pretty much if you have seen all these fancy applications that use visualization and maps and images, probably use leaflet. But I find that at least in my simple example, it could like overlay 5 images on top of each other, and it would be pretty ugly. So I'm just overlaying the geometries right here, and we should get a result any minute now, or hopefully. Oh, yes, right here. So this is our map, these are our results. Leaflet actually must do it. And thank you very much for your attention. We are ready for part 5. Can I hype it up a bit just before Kostas comes in? As Kostas is coming in to set up his laptop. So what we have done here is we have created our knowledge graph. We have loaded into a GraphDB. We created Pythia with this natural language interface. Okay, great. I can go home and do this with my data. Well, again, Pythia is pre-version 0.1. It's not great yet. It will probably crash, but the idea is there. Like, in a few more months' time, it will be there. But what's the problem, you are going to ask? Well, a problem that we encountered while working on, well, pretty much everything we have worked on, is that, okay, let's say that we have GeoSparkle or STSparkle, that's great, and I want to do a lot of geospatial calculations. So, for example, I want to say, give me rivers in Greece that pass through towns which are adjacent to forests. Nice. Now, if there are like 300, 400, 500 villages in Greece, who knows how many rivers, who knows how many forests? You need to calculate, do geospatial calculations between all of these things. So you need to see which rivers are in Greece, which rivers pass through towns, like do all these kind of stuff. And the problem here, of course, is that geospatial calculations are very expensive. They are not cheap at all. So you end up with having to wait for 1 minute, 2 minutes, 3 minutes, not for Pythia, not for the question answering engine, for Sparkle. You need to wait for GraphDB to be able to answer your query, as Kostas will show you.
We are talking about a very, very simple knowledge graph. Okay. This is an example query. It's the final query of the presentation of part 2. And you see that even in this toy knowledge graph, which is like 15 megabytes of data, it's like nothing for geospatial data. It takes 20 seconds to run. Okay, it's slow because geospatial calculations are expensive, and most geospatial triple stores and geospatial databases are not that well equipped to run these kinds of calculations. So what do we do, as Sergios already said? We pre-calculate them. Okay, what we usually do in computing, in computer science, when something is very expensive, we store it in the disk. Okay, and that's what we're going to do in this part 5. We don't have that much time, we have only 10 minutes for this part, so I'm just going to show you our tools and how you can easily do that with this. Okay. Okay, we don't have internet. Okay, so very briefly, we are using Jedi Spatial. It's a tool developed by our team. It's one of our oldest tools. What this tool does, basically, it finds all these expensive relationships between geospatial information in our database. So intersections, as Sergio showed, containment, if they're not contained, if they're not touching each other, if they are touching each other, things like that. Okay, so basically geospatial information. And it stores this information as triples, right? Because we are talking about RDF graphs, about knowledge graphs. Everything is a triple. Okay, so instead of doing these calculations with a geosparkle, like here, you see, we call this geosparkle function, right? As if intersects. What we want right now is to create a triple, okay, like this one. We say that a point of interest has a geometry. Okay, what we want to do is to create a triple that says this point of interest intersects with Sentinel. Okay, we create these kinds of triples and we store them into a knowledge graph. Okay, so for this part of the tutorial, we have the binaries saved in the directory part 5. They're Java binaries. You need Java 8 to run them. I'm just going to showcase them very fast. I know we don't have a lot of time, so I'll just give you these examples. The result of this pipeline will be another small RDF graph with these relationships. And this knowledge graph we can just import in GraphDB and use it as we use the previous datasets. Okay? So what I did now is we want to create relationships between the Sentinel images, okay, and the rest of the geospatial information that we have in our graph. What is this information? It's the rivers, the points of interest, and the city of Hamburg. Okay, so we separated these files, okay, into a group of Sentinel images and a group of the rest of the geometries. Okay, so that's basically what we did. This little script, the Jedi Spatial pipeline, basically prepares the data to be processed by our Jedi Spatial tool. Okay, so after we've done that, we create a file for our output. Okay, so that's where the output of the Jedi Spatial will be stored, and we can run the app. This app is only available in the command line right now. We simply input our source and target datasets. They're in CSV format. Jedi Spatial works better with CSVs. That's why we transform them into CSV. We give some statistics about each CSV file, and then Jedi Spatial performs these calculations and so on. Okay. And now, to understand how expensive and how much these calculations can increase our database, even with this small data set of like 10 megabytes of information, and the actual geospatial information of our knowledge graph is around 2 megabytes of data, the calculations here are about 60 megabytes of data. Okay. There are a lot of calculations, they're expensive, and sometimes, we need to find which relationships we need. There are a lot of trade-offs, there's always this trade-off of speed versus disk size. And right now you can see how many detected links are, how many of these are covered by, how many of these are intersections, how many of these are overlaps, etc. Okay, these are the geospatial relationships that we discovered using our tool. As you can see here, as I said, we created a lot of triples. What do these triples say? That this resource intersects with this resource. That this resource overlaps this resource. Okay. Intersections, overlaps, within, these are the kind of relationships that we have. Now, this data set, we can import in GraphDB. And in a bit, it should be stored in our database. Okay. And we just need a small step here. We are going to use Ghost. Ghost is just a transpiler that transforms our queries from this format that uses these geospatial functions. It basically removes these geospatial functions and replaces them with triples. Okay, with the triples specifically that we created for these relationships. So if we run this command, the command I have in the tutorial is with the last and most expensive query that I showed you in part 2. Okay. And it will give us output the query, the rewritten query that has these intersections as triples right now and not as geometries. You can see here, right? There are just these triples. Okay. Now we can run this query and it will give us the results. And you'll see that it will be much, much faster with this pre-calculations. See, it ran in like in less than a second with this optimization. That's it for my part. I was in just 10 minutes, so everyone is happy, I think. Is there any question for that? For the materialization? No? Okay. Keep in mind, oh yeah, please.
How many images of the TerraQ do you have in this index? Because we have 100 million images.
Yeah, okay.
Then if we do this, graph pre-matching, it will be huge.
Oh yeah, absolutely, and that's something that we have to keep in mind. And I was about to say that this is an optimization that even larger companies use. You can't do anything else right now, right? Because these are very, very expensive calculations, and you either, you take the bullet and you calculate them on runtime, which is very expensive. Some of these queries just don't run, right? They're very, very expensive. Or you just store them in the disk. And sometimes the cost is very large. In one of our projects, our initial data size was around 10 gigabytes, and the complete graph at the end of the project with the materialization was more than 300 gigabytes. But it was necessary, if you want the user to have responsive queries, you'll have to sacrifice the disk size. So it's always a trade-off. What you can do, however, is to specify the entities that you want to match, right? we don't want to discover every entity, every relationship. For example, you can say that I only care about the relationships between Sentinel-1 images and rivers, for example, for a specific use case.
Cost Copernicus, data, so we would need to have multiple those, not the rivers only for Sentinel-1, but a lot of things for everything.
Yeah, absolutely. What we did for our use case, for example, with we were working with satellites as well. Keep in mind, we pre-calculated everything with everything, right? So you can have that. So you can simply, if you give in the JDA special tool as an input and as a target the same file, it will calculate everything. No, everything with everything. That's that. But the more things you calculate, the more disk size you will sacrifice. That's basically it. It's a trade-off. It's a trade-off. Mm-hmm.
As you have always the same tiles, you need just to calculate for the Sentinel-2 tiles, not for all the images.
Yeah, for the time.
Yeah.
The Sentinel-1 is more complex.
Yeah, because the shapes are different.
On the other side, with clouds, you would like to have only what is visible on. So you need to do cloud masking. First, you need to remove parts that are not visible, and then this won't be a tile. If you have it, would like it to do it properly. You should tag only for the product the parts that are visible on the specific scene. Yeah. So, but I agree with tiles would be much easier because you have like finite numbers of.
Yeah, absolutely. Okay, Sergius has a last 5-minute call for some things. I leave the things to him.
Buy me some time, Kostas, buy me some time. Do something entertaining. Okay. Έκλεισα τα slides μου. Thank you, Kostas, for the beautiful presentation. I forced you to clap here. Applause. So, okay, now for the final part of our tutorial, a bit of community outreach. So, Pythia, pros and cons of version 0.1, as I said, will be released shortly. And so, the good things, the successes are that it is actually truly, yes, knowledge graph agnostic question answering. It's one of the, you can count the amount of systems that have tried this in the fingers of your one hand, of a single hand, and achieves new state-of-the-art performance in most benchmarks that we have tried. And we have tried pretty much all of the popular ones. It is plug and play, it does not require modifications. It requires some amount of technical skill to deploy, but we want to improve that. So, the known limitations. Setup and execution requires interacting through a terminal interface. As you saw it, if you are not technically inclined, you would have a hard time unless you exactly follow every step. But then it would be kind of difficult to just, be like, I don't want anything to do with programming, but I have this knowledge graph and I want to take this tool and just see if it works, just see if it works. So this is an accessibility problem. Also, it requires some amount of human intervention during setup. Again, this was a compromise that was made because there was not enough time, and it allows us to focus on more pressing matters. But in the end, we don't want any human intervention during setup. We just want to say, okay, this is my knowledge graph. Then it takes however time it needs, and you can start querying. Also an accessibility problem. Now, for the performance limitations, our prompts and code base require optimization to improve accuracy and response times, and there is a lot of low-hanging fruit left on our architecture. So, we have a lot of things to improve. We can make Pythia perform better, we can make Pythia perform faster, We want it to become an accessible, plug-and-play, no-compromise solution for question answering over any knowledge graph, and a solution that is deployed and used in the real world, not just in academic benchmarks. Because something that really pains me is that we do stuff and we release our papers, and then the only thing that somebody else uses your stuff is when they release their paper and they cite your stuff. And this feels kind of bad because you did all this effort, but you want to see these things actually do things. So, how are we going to achieve that? So first of all, we use Pythia in multiple European projects. So recent development is supported by European projects and targeted at them. Right now, we are participating in both Stellar and Fair to Adopt. Largest releases will integrate improvements and innovations based on our work for the use cases of these projects, on research, on open problems that we find. And yeah, but we also want to have a community. We want Pythia to be software that, okay, of course, you cannot expect a small research team from Athens to make a production-ready and state-of-the-art software and everything at the same time. You need a larger team for that, but we want to at least have Pythia positioned in a place to be that, okay, I have this idea, I have this system, and I believe that a question answering system would be good here. So we want you to be able to go there, take this software and easily test out your ideas to see if your architectures make sense, to build prototypes using question answering, to make question answering approachable at the small scale, for small groups, for smaller projects. We believe that there is a gap there and that this will be very useful. So to do that, we aim to actually respond to user issues. So we really do prompt you to use it, to just check it out. If you are interested, you can send me an email and I can let you know when the software is released. If you use it and have a problem, you can write an issue or send me an email, or if you're interested in collaboration or anything, or have your own use cases or problems or real world issues that you think that something like this would be a good fit, do reach out. And of course, we are trying to use versioning. As you see, we are starting from the beginning to use normal releases, normal development practices that make software that is not just research software that nobody wants to touch ever again after they release their paper. And now, finally, we also aim to focus a bit on accessibility. I have a strong background on developing GUI systems and accessible interfaces for various open source projects. So I am planning the following things for version 0.2. Performance improvements for all components. This is the scientific part. My PhD research is on knowledge graph question answering and knowledge graph agnostic knowledge graph question answering. But also for the more fun and more user-friendly stuff, we want to build a graphical user interface for setting up and deploying Pythia, so avoid the terminal essentially as much as possible. And we're also planning to develop a chatbot that uses Pythia as a graph rag system. So essentially a little LLM that has grounded knowledge on knowledge graphs, that you can select your knowledge graph and just chat with it and actually have reliable and explainable answers that you can be certain about, instead of just being, oh, I don't know if this is correct or not. For that, it's probably going to release it late November. And thank you very much for being here today. These two QR codes will lead you to our website and our group's LinkedIn. If you are interested, please follow us. You can also go to the tutorial, GitHub or Pythia or Topos, and whatever you found interesting or nice, either send us a message or drop us a star or a watch on our GitHub repositories. We will improve the materials. I have not added some things, but I will add them when bids finishes, and don't be afraid to share them with anyone, and just so you know, if anyone's interested, just let them know. Thank you very much for being here, and thank you to my colleagues. Have a nice bids. You are free to go. You don't want to go. Oh, we're family.